In this lecture, we're going to look at a different approach to machine learning called lazy learning. So I'm going to talk a bit what lazy learning is and then give you three examples. A classifier, k-nearest neighbors classifier, a regression method, kernel regression, and then something that is unsupervised learning, but I'm going to include here because it's another example of lazy learning, which is kernel density estimation. So let's start with this idea. So far, we have seen an approach to learning called eager learning, where we represent the hypothesis class with a model with parameters, and we train this model by fitting the parameters. We instantiate those parameters, we adjust them, and once we have our final hypothesis described by the model instantiated with some specific parameters, then we can discard all the training data, because now for any question about predicting new examples, we can answer it based solely on the model and the parameters. So basically the hypothesis that we have learned at the end of this process. This is called eager learning because the first step is to try to find that structure in the data represented by the instantiation of those parameters in the model. So once we have the final hypothesis, we already assume that we know everything we need to know, and from then on we can just discard the data and make the predictions based on the hypothesis. With lazy learning, we do not have this training step. We are not going to use a model to represent the hypothesis class. We are not going to adjust parameters and try to obtain a specific hypothesis. We simply keep the training data, the training set, and only when somebody asks for a prediction on a new data point do we look up the training set in order to figure out what to answer. So basically, the idea here with lazy learning is that during the training step, we don't do anything. So in fact, there is no training step. We just store the training data. So let's see an example of this with k-nearest neighbors. The idea of the algorithm is that given a training set where we have features and the class labels, this is a classification problem, we just store all the training set. Then when we need to predict the class for a new point, we look up the training set to find the k closest examples that we have in the training set, those that are closest to the point we want to predict, and then we predict the class for this point by the majority vote of these k examples that are closest to it. This is lazy learning because we don't have a model to represent the hypothesis class. We don't have a training step. We simply store the data. We are not trying to fit any parameters. And only when the query comes up, when we are asked to predict something, do we then consult the data and use this algorithm to make the prediction. So this is an example of what happens if we have this training set. The blue points belong to the blue class, the red points to the red class, and you can see here, if we use a k value of 1, we have what is called a Voronoi tessellation, which is a partition of this plane, in this case, because we are dealing in 2 dimensions, where we assign each region to the point that is closest to it using Euclidean distance. So you see between these 2 points, we have this line right in the middle of them that determines that on this side we are predicting a blue class and on this side a red class. The same thing for these points here. So basically, if we use k equals to 1, the algorithm consists in, given a new point, for example over here, we find the closest point in the training set and we label the class with the same class as that point in the training set. So this gives us this kind of tessellation, and the discriminant will be this series of straight lines separating the 2 classes here. If we use larger values of k, for example 3 or 5, we have more complex tessellations, but the idea is the same. Now here things are a bit different. For example, we have red predictions here, even though there is a blue point on this position, because if we take the 3 closest ones, For example, for a point here, the 3 closest points would be 1 blue and 2 red. So this counts as red. Only when we reach this side where we have closest points here on the blue side do we start predicting the blue class. And this is the same thing, but using 5 closest neighbors, the 5 nearest neighbors instead of 3. So usually we use an odd number of neighbors when we have 2 classes, because this prevents having a tie. So we don't have any ambiguous case where we have the same number of neighbors of each class. In all these cases, this discriminant, the decision boundary here, is piecewise linear. That is, it's composed of straight lines, but it is a set of straight lines. The exact shape will depend on the number of neighbors and the distribution of the points, of course. But if we use Euclidean distance, then we have always this piecewise linear decision boundary. If we use a higher value of k, then our discriminant becomes less dependent on local conditions. For example, with a k value of 1, this means we are assigning to each point the prediction of the class is the class of the closest point in the training set. So in this case, we have a very curvy frontier here, because it can snake around all of these different points here. If we use, for example, the majority vote of the 25 nearest neighbors, which is this example, then we have a stiffer frontier that cannot curve as much, because now we are looking at a larger neighborhood and using the majority vote there. So, for example, even though there are red points here, the majority of the points around this area are blue, so this becomes part of the blue region too, and the whole frontier becomes much less curved than the one using just the closest neighbor. So what we need to do to implement a k-nearest neighbor classifier is we need a distance function first, so that we can find the closest neighbors. If we have categorical data, we can use something like Hamming distance, which gives us distance of 1 if the categories are different, or 0 if it's the same category. But if we have continuous variables, for example, in this case, the coordinates of the points, we can use, in general, this Minkowski distance, or p-norm, which has this general formula. The p root of the sum of the modules of the differences in the continuous features raised to the power of p. So if we are using Manhattan distance, for example, then p equals 1, and we just have the sum of the modulus of the differences. If we use Euclidean distance, which is a common distance measure, the p-value is 2, so we have the square root of the sum of the squares of the distances. And this is generally what we use to compute distance between coordinates of points. Of course, you can use any value of p in theory, but often these are the most used ones. They are more intuitive and usually more adequate to the kinds of problems we're solving. So this would be an example of using k-nearest neighbors with k equals 1 and p equals 2 on the Minkowski distance, that is using Euclidean distance. If you use p equals 1, you have Manhattan distance, so it will give frontiers like this, because now we are considering only the modulus of the difference between the coordinates. If you use, for example, a p equals 0.7, you have something that starts becoming a bit strange. So usually these other values for the Minkowski distance, although in theory we could use them, in practice they become very unintuitive, so they are not generally used. So how can we implement this? To look in detail, let's start by defining the distance function. So this would be a Minkowski distance with p equals 2 by default. Note that in Python you can do this on the parameters. If you give a value to the parameter here on the signature of the function, then if the argument, the corresponding argument is omitted, this will be the value that this variable takes in the function. So this will be a default value. If the argument is given, then the value given in the argument will override this value, and the variable takes that other value. So this function receives one vector with the coordinates of one point, the matrix with the coordinates of all the points in the training set, and by default it uses Euclidean distance, so p equals 2. Now what we can do is to take advantage of the broadcasting features of NumPy. Since this is a NumPy matrix, when we subtract the vector with the coordinates, if the number of columns in this matrix matches the number of elements in this vector, this operation will be broadcast over all the rows on the matrix. So we get the differences in all the coordinates for all the points in the training set relative to the point we are trying to predict now. So we raise this to the power of p, taking the absolute value of the differences, and then we sum all of that and raise to the power of 1 over p. So basically, this is just the implementation of this equation, of this expression here. So we return all of these distances. This now will be an array of the distances between each point in the training set and the point we're trying to predict. And the reason why we obtain that is because in the sum we provide this second argument that indicates that the axis where the sum will be made is axis 1, that is the columns of the matrix, of this matrix. So what we get is one sum for each row in the matrix, and this gives us one distance for each element in our training set. So this is a vector with all the distances between the points in the training set and the point specified by that x here. This is one convention sometimes used where a single vector is lowercase and a matrix is uppercase. So I'm just following that convention in this case. Now we need to find the nearest neighbors. So given point x and the matrix of training points x, uppercase x, we want to find the k nearest neighbors. So we get the vector with the distances, and then we obtain the indexes that would sort this vector in increasing order. So this argsort gives us the positions, the ordering of the indexes of the vector that would sort it in increasing order. And now we just return the k first indexes of the vector. So this way we know which are the k closest points to the point we want to test here. So to classify point x given this training set in matrix uppercase x and the class labels in y, using the k nearest neighbors, we just get the k nearest neighbors using that function, and now we return the class that has the majority in this set of k nearest neighbors. So from the class labels we take those indexes corresponding to the k nearest neighbors. These are the class labels for those points, and now we return the mode of this array, that is the class label that is in a majority. Now the mode actually returns two arrays, first the modes and second the count values, and each of these arrays gives you the value of the most common element, the second most common, and so on. So I'm going to use the first of these arrays, which is the modes, and the first element of that array, which is the most common label. So this gives us the most common label in the k nearest neighbors, and this is what we can do to implement a k nearest neighbors classifier. Note that there is no training stage here. We just need to provide the training set, and at query time the algorithm picks the closest examples and gives us the majority class of those examples. Now, one problem with the classifiers and the regression and so on that you saw so far is whether or not we should rescale the data. So in general, you should rescale the data because you can have features of different types. for example, age in years and height in centimeters and weight in kilograms. So it doesn't make sense to compare 1.7 meters with 85 kilograms because the scales and the units are completely different. So in that case, for example, standardizing everything so it has a mean of 0 and standard deviation of 1 would be a good idea. However, if you have features that are in the same units and represent the same thing, for example, coordinates measured in meters or degrees or something like that, then if you rescale the data, you are going to cause distortion in your positions, your coordinates, and if you are using distance functions, then things will be different from what they would be if you did not rescale the data. So in general, we should rescale the data when we have different units of measures for the different features, but sometimes we need to take care to avoid distorting the data if we rescale independently the different features. Now, one problem we have here, just as we saw with previous classifiers, is to find the best hyperparameter here, the best k. So we are looking for the best hypothesis class, in a sense, because using different values of k gives us different combinations of lines on the frontiers that we can find. But we don't have an explicit model. So we are not really trying to use the best model. We are just trying to optimize this parameter. So let's load an example set, this one. We save a third of the points for a test set. We're not going to use that one, just to estimate the error, the true error at the end. And we're going to use cross-validation for evaluating different values of k. So we're going to only use odd values of k to avoid having a tie between the class labels. And we're going to measure the error as 1 minus accuracy. So basically the fraction of points that are incorrectly classified. One important thing, I'm going to show the test error here on the graph, but we are not going to use it to make any choice. It's not a problem to look at it. It doesn't become biased just because you look at it, but it will become biased if you use it to choose the k value in order to minimize the test set, so the test error. So in that case, it will no longer be a test error, it will be a validation error. Okay, so this is the validation error obtained with cross-validation. This is the average over a number of folds. This is the training error, also in the average in cross-validation. And this is the test error here. Now, the test error happens to be below the training and validation error. This sometimes happens because if by chance you choose points that are easier to classify, or most of them are easier to classify, then you can have a lower error than you have in validation or training. But in any case, we are not going to use these values to pick the best model. We are going to use these ones because these are the validation error. So in general, you don't even plot the test error. It's not useful. You just compute it at the end. But one thing that I would like to call your attention to here is the profile of the error. We saw previously, for example, when we are increasing the expansion of the data into higher dimensions in logistic regression, we saw that we started underfitting and then we went to overfitting when we reach a very high dimension. But here, when we have a very low value of k, that's when we are overfitting. And this intuitively can be understood because if we use a k value of only 1, we are just looking at the closest point in the training set. So we will never make mistakes on the training set. As long as there are no points completely overlapping, if we are checking the error on the training set, the closest point on the training set is always the same point that we are checking. So we have an error of 0 on the training set. On the training error will be 0. The validation error can be much higher because now we are only looking at one nearest neighbor, at the nearest neighbor, and this can lead to a lot of overfitting. So you can see that we start by overfitting, but as we increase k, then we increase the training error, but we start decreasing the validation error. So somewhere around here, we can find the optimum value. And so we have this one with k equals 9. So now the training set will be the full training set, the training data that we're going to use to make new classifications, and we can apply this to the test set. Note, however, that I'm calling this the training set just because it's the data used to find the labels in order to make the predictions, but we are not actually having a training step in the sense of optimizing parameters. We just store all the data in the training set, and then we predict the value for each of the test set using the data that we stored. Now, one thing that comes with this kind of distance methods is this curse of dimensionality, which arises as we increase the dimension too much. So basically, what we have in these distance methods is that we define some region by a frontier. For example, this frontier here, where the distance to this point, this blue point, and this red point is the same. If we are only in 2 dimensions, then this frontier will be a small part of the whole region. Most of the points are inside the region, and few points are close to the frontier. However, as we increase dimension, we start having a larger fraction of points close to that frontier. For example, if you imagine that the border is only 5% of the diameter of the region, then in 1 dimension, in a single line, the border will occupy only 5% of the points. But if you go into 2 dimensions, then by using this 5% of the diameter all the way around, for example, a circle, you get this ring on the outer edge of the circle that occupies about 10%. In 3 dimensions, you have a shell on the outer edge of the sphere, and this will occupy around 14% of the volume of the sphere. And as you increase the number of dimensions, this region close to the frontier, close to the edge, will start to become the majority of the hypervolume that you have. So if you are in, for example, 20-something dimensions, then you can have more than 70% of the region very close to the frontier. This means that when you are trying to classify points based on these distance methods or in establishing these frontiers, when you go to very high dimensions, you start having this problem that everything now is in the frontier, so you start having more errors in discriminating between the groups. So in general, it's not a good idea to have too many dimensions, also because of this problem. Okay, so now let's move on from classification, lazy learning in classification, to lazy learning in regression. We can do the same thing in regression. Instead of having an explicit model where we fine-tune the parameters, we can just store the data, the training data, and then use k-nearest neighbors for regression. So basically, the prediction of the value at each point will be the average of the values of the k nearest points. If we use k equals 1, then we just look at the value of the nearest point and use that one for our prediction. So this would be an example with k equals 1, the regression using these points in red. If we use k equals 11, we are taking the average of the 11 nearest neighbors, so we have a line that is a bit smoother and goes between the points. But the idea is the same as with k nearest neighbors. We look at with k nearest neighbors for classification. We look at the nearest neighbors, the k nearest neighbors, and we aggregate the target values for those in order to make our prediction. Of course, this is has this problem here that we have all these steps because we have discontinuities when we switch from one neighborhood to the other. So when we lose one point in the k-nearest neighbors and substitute that one with another point. We can make this smoother if we use kernel functions. So instead of using the nearest neighbors and just averaging, because this gives us a discontinuous prediction function, we can replace this with a continuous function that will give less weight to points that are farther away and more weight to the points that are closer together. So this is called kernel regression in this case, because we're going to use a kernel function. And the definition of a kernel function is any function that, in this context, is any function that meets this criteria. It must be non-negative everywhere, so it's either 0 or greater than 0. It must have an area of 1, so when you compute the integral for all the x, it must be 1, and it must be symmetrical in the x equals 0, or so k of minus u must be equal to k of u for any value. These are some examples of kernel functions. You can use a Gaussian curve centered here at 0. You can use a triangle, a rectangle, things like that. So all of these, the cosine function and so on, all of these meet those criteria in that the total area is 1. They are symmetrical, so the value here, for example, at 1 is the same as the value at -1, and they are non-negative, so they are 0 or more. And this allows us to use one of these functions to give continuous weights to different points, depending on how far away they are, and produce a smoother regression in our predictions. So let's take, for example, using a Gaussian kernel. This would be our kernel function. Now we need to aggregate the contributions of different points based on this kernel function. So one simple way of doing this is the Nadaraya-Watson estimator, is just to compute the y value for some point x as the weighted average of all the y values of all the points in the training set, each one weighted by the kernel function, taking the distance between that particular point t and the x we are trying to compute. So if we use a Gaussian kernel, if we go too far away, we start having a very small contribution. If we are closer to the point, we start having a larger contribution. We can include this smoothing term here, this bandwidth parameter, that if it's large, it makes this term smaller, even for larger differences. So it means that even points that are far away will still contribute significantly to the value of y. If we use a small h value, then this magnifies the distance we are finding here, and so only points that are close together do have a significant contribution. There are other estimators. I'm just giving here an example of Priestley-Chow estimator, which we can use if the points in the training set are not equally spaced. So we calibrate these estimates also by the difference between consecutive points in the training set. This is often used for time series, for example, when we have samples taken at different time intervals, so we can compensate for that. But the idea is the same, is to aggregate the contributions of all the points using this kernel function, for example, the Gaussian kernel, to determine how each point contributes to the estimate. So here is an example of how we can implement this. This is just the function for the Gaussian curve, the one that we have here. So we receive some value u, and we output the value of the kernel function for u. Now this u will be the difference between the point we are trying to predict and the point in our training set, divided by this bandwidth parameter. This is what we can use to determine how strong is the effect of the nearby points with respect or comparative to the points that are further away. So we can do this using broadcasting. If we send a vector here, this will return a vector with all the kernels computed. That's what we do here. Again, we have the training set here. We have this is a vector of x values. We have one x value here. We compute the difference, so we have the difference between the x we're trying to predict and all the x values of the training set. So we can compute these differences like this, and then add so we could use broadcasting. I'm sorry, in this case we are not using broadcasting. I'm doing this one at a time, but in any case, this could also be a vector if you want to use this Gaussian function for vectors. But in this particular case, I'm iterating through each element on the training set, computing this difference, the kernel for that particular distance between the point we're trying to estimate and that point in the training set, and then adding this numerator and denominator here on the Nader-Watson estimator so that we do a weighted average. Each y value on the training set is multiplied by the value corresponding to the kernel for that particular distance, and then the sum of all of these is divided by the sum of the values of the kernel for all the points in the training set. So this gives us a weighted average in which the weights are the values given by the kernel. So the result is like this. If we use a small h value, we are making the Gaussian curve fall very quickly with distance. And so for small h values, our regression becomes very close to the points and much more curved. If we increase the value of h, then we are giving more weight to the points that are farther away, and so the curve becomes a lot smoother, and this way we can control how smooth and how curvy our regression line is. And note that in this case the regression is continuous because the kernel function here is a continuous function and gradually goes down as the distance increases. So when we add all these contributions, we still have something that does not have those discontinuities, those steps that we saw with the k-nearest neighbors regression. Okay, another method for another kind of lazy learning method, also based on kernels, is kernel density estimation. In this case, this is an unsupervised method. So we are not trying to predict some label that we have on our data. We are just trying to represent or estimate the distribution of the points. We can do this, for example, with a histogram. Suppose that we have this set of points here. There are more points condensed in this region and others spread out here. And we can do histograms. We can do a histogram with a larger bin, this one in yellow. We can do a histogram with a finer bin size, the one in green. But one problem with the histogram, although it gives us an idea of the distribution, is that it has all these discontinuities and it can change a lot depending on how we set the bin, the size of these regions here where we're going to count the number of points. So we can make a continuous estimate of the distribution density by using a kernel function. So basically what we're going to do is, for each point, we're going to consider a kernel function centered on the point, for example, the Gaussian curve again. And what we're going to do for the density estimation is just to sum the values of all these Gaussian curves. So instead of having these discontinuous bars that we have in the histogram when we count things, we have this continuous function that we obtain just by adding all of these kernels centered on each of the points in our data. Now we can do this lazily because we are not going to define this value. We are just going to store these points, and if someone asks us what is the value of the kernel density estimation at this point here, we just compute the values of the kernels here, add them up, and we get the result. So we don't do this on a training stage. On the training stage we only store the data. This is lazy learning, and only when we are queried about the value do we compute the result. So this you can use in scikit-learn. You have the kernel density class. You use fit, the fit method. This is standard in the scikit-learn interface, but note that fit is not really fitting anything. It's just storing your training data. It's when you compute the scores for all of these samples, for example, in the test set, that you get that the object will do the computation and give you the values for the X values you provide. So this is lazy learning because there is no fitting of parameters on the first stage. Everything is computed on query time. Okay, so to sum up, the idea of lazy learning is that we don't have an initial stage of computation where we are fitting parameters. We just keep the training data and then obtain the results based on that. So basically, if you have a classifier or a regression model or some kind of predictor or estimator that needs to retain all the training data in order to be able to answer, this is basically lazy learning. It means that it's not computing the necessary parameters first, so it's doing the computations when you ask for the results. We saw this in classification with k-nearest neighbors, in regression, also using k-nearest neighbors, and also using kernel methods. So either for regression, where we use a kernel function to weigh continuously the contribution of different points, or in kernel density estimation, where we add the values from these kernel functions so that we have a smooth estimation of the distribution density of the points. So to read a bit more, you can see these sections here in these textbooks, Alpiden, Mitchell, and Marsland. You can see descriptions of the k-nearest neighbor classifier and these kernel methods.